My name is Raj Lakhani. I'm from Peri, India. We have three fantastic speakers here on the dais. I have the pleasure of inviting Mr. Peter Oborn, who's the Deputy Chairman of Aedas Europe. Mr. Peter Oborn is going to talk to us about facades, and he's also got a special interest in management of the Research and Development Group. Please join me in welcoming Mr. Peter Oborn.
Good afternoon, ladies and gentlemen. I'm going to start with an apology to you and also to our chairman, because I've done what no speaker should ever do, and that's to make some last-minute changes to my presentation. And the reason for that is simply that when I was first invited to speak by Anthony some months ago, we just completed our proposals for a project in Abu Dhabi for the Abu Dhabi Investment Council, which I thought would be of interest, and which I'm going to present. But as I've sat through the sessions over the last couple of days and listened to the extraordinary work being done by Remaking of Mumbai Federation, and yesterday toured the Sea Ward, I was struck by the challenge facing Mumbai. The size of the challenge is overwhelming. The complexity is bewildering. The scale, how one can kind of zoom in and out from the macro to the micro is quite extraordinary. The need to overcome inertia and to develop a momentum, all of these considerations left me with a question. And the question was simply this: how does one be sure of ensuring a successful outcome? It was a question that sort of troubled me overnight, and I, as I say, made some changes to my presentation, which I apologize for. But it struck me that in order to know whether you're going to have a successful outcome, you need to be able to recognize it when you see it. You need to know how you're going to tell if you failed, and you need to establish some parameters for success. And if you're able to do that, then you can use what we've now developed in Europe, evidence and performance-based design tools to help simulate outcomes and prevent failure. So the office for which I'm responsible in London is also home to the Practices Research and Development Group, whose work focuses on three principal areas: sustainability, advanced modeling, and computational design. Computational Design Group develops bespoke solutions for helping us to work with this complexity, and I thought it might be interesting if I quickly showed you some of its recent work. Yesterday, we heard one of the speakers talking about the new line that's to be built from east to west in Mumbai, and funnily enough, we're doing the same in London with a project called Crossrall, an extraordinarily complex project that's looking to knit a new rail network from east to west in London, obviously knitting itself through all the foundations and services that are found beneath the city. But a remarkably little amount of work had been done about what the consequences would be for this above ground, and we were actually employed by Transport for London to take a look at what the sensitivity would be of moving the station entrances of a station that we were responsible for at Whitechapel, and how this would affect people movement around the city. This application that you're seeing running now demonstrates what the impact of changing the station entrance would have on the city above ground. A subsequent piece of work which built on that last piece of work was to look at what people's experience would be as they moved around the city, and what they would actually see as they made their way to the station. Again, the impact of this may not be immediately apparent, but in an established capital like London, where land prices and property prices are so high, the more prominent a street frontage is, the more highly rated its retail value is likely to be. Equally, from the perspective of security, one could at least then begin to get a measure of those spaces that were going to be less heavily visible and less well supervised. Here in Sevenoaks, outside London, we were tasked with preparing a master plan for a very sensitive site in an area of outstanding natural beauty. And we were actually engaged 3 years after the previous design team had finished its work, and we were presented with a huge wealth of information to manage and try and get our heads around. And in order to help us do this, we developed a Java application, which you can see here, that allows us to turn off and on layers of information in terms of survey information. And there's another section which deals with the analysis, and another section again which deals with the proposals. And this Java application was available to all members of the design team, the client, consultation groups. So we kind of democratized the flow of information and allowed people to see what we were doing, and it helped us understand the problem much more effectively. Another consideration on this particular site was the visual impact of the proposals. The proposals, as I said, lie in an area of outstanding natural beauty and surrounded by an ancient woodland. Tremendous constraints in terms of visibility of the site, and we developed an application to help create an envelope, a planning envelope, so that we could demonstrate to the planners and stakeholders that the development wouldn't extend beyond the visual envelope. And as we zoom in on the individual plots, or the clusters, as you refer to them here in Mumbai, we were then able to set planning parameters for each plot. So again, allowing us to kind of determine predictable outcomes. And this, which looks a little bit like a computer game, actually isn't a computer game. It's an application which, again, allows us to distribute mixed uses around the site according to optimum adjacencies. And I would stress here, this isn't a design tool in the sense of it produces finished designs, but it allows us very quickly to get from a standing start to a position where we can make informed decisions about the optimum location of facilities. For example, locating the housing for the elderly adjacent to transport nodes, for example. And then finally, I think Masdar has been spoken about a number of times during the course of this presentation, and we're currently working at Masdar on what's known as the Mist neighborhood, which is a residential component. It, as you know, in its bid to become a zero-carbon city, it's set a stringent set of key performance indicators, one of which is passive solar shading, where there are some very strict criteria established in terms of passive overshading. And we, again, developed this application here to demonstrate how we were going to meet the particular key performance indicators which the client had set. And actually, interestingly, as a result of producing this tool, we were able to challenge the parameters which had been set by the client, which is another interesting aspect of this work. Now, I'm not suggesting that any of these particular tools are necessarily appropriate here in Mumbai, but rather that techniques exist to enable those involved with problems such as the remaking of Dubai to deal with complexity and achieve more predictable outcomes faster. So, returning to the theme of my presentation, I'm going to briefly present our concept for a new headquarters building for the Abu Dhabi Investment Council, and in so doing, illustrate how we've combined a range of computational design techniques together with a reinterpretation of some traditional design approaches to create what I have perhaps provocatively referred to as a new vernacular, or perhaps what Anthony was referring to yesterday when he talked about tall buildings with identity. The client's brief. We were invited to submit a competition entry for the new headquarters building for the Council towards the end of 2007. The Council is one of the Emirates' several sovereign wealth funds, and its aspirations for the new building were set out in a concise but aspirational document which sought, amongst other things, the creation of a landmark building. The aspiration of the brief was made all the more exciting because of what was also happening in Abu Dhabi at the time. The government had recently published the Abu Dhabi 2030 plan, which creates a development framework based upon the principles of cultural and environmental responsibility. The Masdar initiative, which we've talked about, which seeks to place Abu Dhabi in the forefront of the development of renewable technology, was gathering momentum and receiving worldwide press coverage. And the Estidama environmental standard, a localized version of LEED, was about to be published. There was also, of course, the context created by the great Islamic architectural tradition, together with the region's vernacular architecture, which provided a number of clues for dealing with the severe climate. And then, of course, there was a site, an analysis of which provided information about a range of issues, including access, aspect, and orientation. Solar analysis demonstrated the high levels of exposure which could be expected, particularly around the north-northwest and north-northeast, so very high levels of solar gain. So as we began to think about our design approach, we identified the importance of three key drivers: inspiration from nature, or what's become known as biomimicry, sustainable design, and the principle of Islamic architecture, a key aspect of which is geometrical composition. A geometrical composition, of course, has been a defining characteristic of Islamic architecture for centuries. The circle and rotation reflecting the concept of unity and unification evident in nature, and an important concept in Islam. Evolution of the pattern produces a distinctive aesthetic, which we're all familiar with. So our starting point for the design was two cylindrical towers, a circle producing the most efficient form in terms of wall-to-floor area, maximizing volume with minimum surface area. The following diagram illustrates the manner in which we began to generate the pattern which ultimately created the framework from which the form of the tower was crafted. The geometry generated an articulated plan to provide orientation, a front to rear elevation as it were, and the resulting composition generating node points on the elevation, thus creating a three-dimensional grid. The form of the tower was then sculpted around the core, narrow at the base and at the top, but broader around the intermediate floors. The crown of the tower was cut at an angle in order to minimize solar gain for a bank of roof-mounted photovoltaics, while sky gardens were introduced in the most heavily exposed southerly elevation to reduce solar gain while providing an amenity for users. We then recognized the potential for eroding the elevational grid to generate the structural and cladding concepts, and the resulting honeycomb grid performs well in terms of seismic response with lots of vertical elements, well in terms of bracing, in terms of lots of diagonal elements, and well in terms of redundancy with lots of alternate load paths. At the same time as we were generating the form of the towers, we were keen to find a way of reinterpreting the concept of the popular wooden lattice screening, the mashrabiya, a traditional device used to achieve privacy, reduce glare, and solar gain. We were also keen to explore the potential for developing the mashrabiya concept within the same unified geometry. So, why dynamic? Why make it difficult? Well, until recently, most of the buildings in the Middle East have tended to rely on very high-performance facades. And while most traditional mashrabiya are fixed shading devices, we decided to explore the potential for developing it as a dynamic shading device. You'll see here on the left, the curtain walling in a traditional building in the Middle East has very, very high-performance glass. The quality of natural light within the building, the quality of space for users is quite poor as a result. A reliance on artificial light, whereas with a dynamic shading device, we felt there was a potential to do something a little different. So, as we began to develop our proposals for this dynamic facade, we looked for precedents, and we were reassured when we found these umbrellas in the courtyard of the Medina Mosque in Mecca, designed by Fry Otto and Boda Rausch in the 1980s, which had been operating successfully for over 20 years with minimum maintenance. As part of the competition submission, this doesn't seem to be working. Unfortunately, that's meant to be a dynamic model. But as part of our competition submission, we developed an application, again in JavaScript, which demonstrated how the mashrabiya would operate through the year as the sun tracked around the building. And were this movie to be working, you would actually see the mashrabiya being manipulated by the application, and our ability to determine the month of the year, simulate the maximum and minimum opening angles of the mashrabiya, and thereby visualize the whole component in operation. The application allowed us to take off and to generate drawings of the mashrabiya and to communicate our intentions to the client effectively. We also modeled a section of the facade to illustrate the build-up of the various layers of structure, facade and mashrabiya, all working on the basis of the same node points, avoiding the need for secondary structure, the principle being one of progressive integration. And a preliminary analysis undertaken by Arabs with whom we were working suggested that the mashrabiya would enable us to reduce the cooling load by 20%, which was very encouraging. Of course, this was at that point just a competition entry, but we then won the competition and had to make it work. So amongst the technical considerations that we had to deal with was the detailed facade design. And as you can imagine, the facade design is quite a complex affair with numerous variables and interdependencies: design temperatures, cooling load, glass performance, mashrabiya performance, lighting levels, use of blinds, etc., all of which fed into a single energy model, and has relied on us working very closely with Arup MEP engineers, facade engineers. They have a dynamic structures group and material technologists. One of the first things we did, and relatively straightforward, was actually the facade optimization, which allowed us to optimize the facade in terms of flatness, regularity, deflection, and wastage. The red colors on this facade representing the most twisted panels, by which we mean up to 5 millimeters, and the blue practically flat panels, less than 1 millimeter. At an early stage in the process, Arup had set a solar heat gain threshold of 400 watts per meter, from which we derived the optimum performance of each element of the facade. And use of the mashrabiya has allowed us to greatly reduce the G value of the glass, which is the shading coefficient, and correspondingly halve the light reflectance while doubling the light transmittance. Fabric selection, again, we worked with Arup's material technologists to help select the most appropriate fabric, and ultimately selected PTFE coated glass fiber on the basis of its proven performance in the Middle East. It has high stiffness, good durability, it's got color stability, it's non-combustible, and it's easy to clean. And we found another precedent at the Phoenix Library in Arizona, where the material had been used with little or no maintenance for over a decade. So bearing in mind that we're talking here about a dynamic facade, we needed to think about the operating cycle, and we needed to determine the optimum operating cycle based initially on a 3-position open, mid-open, and closed configuration, although we'll probably end up having 4 or 5. And in this series of slides, we're generating the solar angle from a program called Kinetic, and then transferring it into Rhino for the technocrats using Grasshopper to simulate the sun's movement and the mashrabiya response. No. Sorry, I thought I was going to have problems with that slide. But had it worked, we would have seen the operating cycle of the mashrabiya as it opened and closed throughout the day. Sorry about that. The detailed design of each mashrabiya unit. There are 900 of these units on each tower, so it's important we got the design right, and we developed the detailed design again in Rhino to ensure minimum sight lines, maximum use of repetitive elements. And we work with Arup Materials again to optimize material selection and specification. Kinetic design is a moving object, so we needed to develop the kinetic design to satisfy ourselves that the mechanism wouldn't lock or bind or flex. And we used all of this information as the basis for creating a tender pack confident in the knowledge that what we were seeking would perform, would be buildable, and that we could control the appearance. During the 6-week tender period, 2 of the tenderers took it on themselves to produce a kinetic prototype, not an engineered prototype, and not a visual prototype. This one was produced by the successful facade contractor by the name of Uanda, using leftover pieces of curtain wall material with spray-colored fabric. But it gave comfort to the tenderer and ourselves and the client that the device would actually operate. The sections in the finished mashrabiya will be much more slender than this, so the visual interference will be much less. There were then some practical issues to consider: risk management. Obviously, we were doing something new, and with Arup Dynamic Structures, we adopted the FMEA risk management regime used in the automotive and aerospace industry to design, test, and verify. And we created a testing regime which the subcontractor will be following. The prototype which you saw earlier has already passed 30,000 cycles, which is quite reassuring. Access and maintenance was also an issue in terms of cleaning and component replacement, and with Davis Langdon, who we were working, we addressed that in terms of costs. So was it worth it? Well, the building isn't finished yet, but in terms of the numbers, we've certainly we're going to improve the daylight within the building considerably. We're going to have much less use of artificial light, much less use of internal blinds, a much reduced cooling load, lower energy consumption, and 20% reduction in carbon emissions. So quite a considerable list of benefits. And as I draw to a close, just to say one more thing about the advanced modeling group that we have, because we were adopting a geometrically pre-rationalized concept, this allowed us to develop a series of geometry statements from which we could produce one integrated building model. And unfortunately, it looks like this movie's not going to run either. But I have a still of it in the next slide. Had that movie run, you would have actually seen the application generate the entire building envelope, the building structure, and the mashrabiya from one set of geometry statements. And obviously, having that capability allowed us to tune the design throughout the design development process, and it also allows us to pass very accurate information to the contractor and produce as a tool for use by subcontractors. We actually moved the project into Gary's digital projects later in the project, so that we could do a more advanced analysis. And again, interestingly, we used that self-same model to produce this physical model, which is about 5 feet tall, and each of the individual mashrabiya elements were made uniquely by 3D printing based on that model, which was quite reassuring. So site progress, an enabling works contract started following completion of the design last year, and the main contractor, Alpha Tame Carillion, was appointed at the end of last year. Slip forming of the both towers has since commenced, and the project is on program to complete at the end of next year. Whether it will become a landmark when it's completed will be for others to judge. Thank you very much. Thank you.